Hey and welcome to this tutorial on how to accurately predict stress reduction after yielding. So I will talk about how you can come up with a material model that can predict the stress strain response that you see here. So the response is initially linear elastic, it starts to yield early on, you get large scale yielding and then softening after the yielding point. This can cause necking in the specimen sometimes, but it doesn't have to. It's all dependent on the material. What I will cover here today is not the necking part or the experimental side, but I will talk about what kind of material models can predict this. How can we actually come up with predictions, as you can see on the screen here? The dashed lines look pretty good. They match the experimental data pretty well. How do we do this? What are the choices? And how can you use this method for the materials you're interested in? So let's get started. I will start by simply looking at the experimental data. And in this case, we have two data files. So let's just open them quickly. We'll see they are time, engineering strain, and engineering stress. Here they are, and they are two different strain rates. One is 10 times faster than the other. So let's see how we would set this up. I will just start up calibration, the material model calibration software that we'll use here. I will reset the layout of my window so we can see all the parts of it. And now it starts to look a little bit more realistic. The first step is to read in the experimental data. So I just click on the plus sign. I use an experimental data type, and I will select the data that I have. I'm going to pick the first file here, number 1. I just open it up, and remember time, engineering strain, engineering stress. So this looks good. I'll keep these values here, and I save it. Here's the first one. And then I'm going to go plus sign, and I do to load the experimental file and do the second one. And in this case, also the default values are good. So here they are. You see now that there's plotted here is the true stress and true strain, and the experimental data that we have is actually engineering stress, engineering strain. So I switch over to that by clicking on the E button here. The legend, I like to set up it to be a little smaller font. This is unnecessarily large. And here we go. So this is kind of the experimental data that we want to work with. I'm going to save this as test 1. And let's figure out what material model we can use here. There are a few different choices. One choice that I like for a case like this is the Three Network Viscoelastic model, viscoelastic viscoplastic model. It's a new model in the PolyUMod library, and it works really well for almost all kinds of polymers. And it's very flexible, and it has some features that allow us to predict this kind of response pretty easily. So I will demonstrate that. So I just go to material model TNV, and I say OK, and I get this dialog box that allows me to set up the structure that I want here. And this is perhaps the hardest part of this calibration. If you want to use the TNV model, you need to actually specify what network structure do you want. In this case, I'll start with a 2-network model. So network 1 and network 2. Network 3 is deactivated, and failure models are deactivated. And right now, the first network is a yaw hyperelastic model, and that's good enough. They will be capturing the large strain response. In this case, it's almost flat, so we don't actually need the first network very much. It's just have a little influence, but we'll keep it here just for simplicity. The second network, I will use a yaw hyperelastic network with a power law flow. They are anisotropic flow, but we don't need that in this case. So I say OK. And then we have our model here. I'm going to drag this all the way up so we can see all the parameters that we need. And some of the parameters that we want to use here to capture the reduction in the stress after yielding are not activated by default in this case. So we're going to make some little tweaks here to these parameters in order to figure out what's going on. So let's before we even go there, let's see if we can pull up the theory for the TNV model. And the easiest way to perhaps do that is to just open a web browser, go to PolyUMod Three Network TNV model here, and we get a little page that has information. So this model has 3 parallel networks. In this case, we deactivated the last one. So the first one has a spring, and the dashpot is deactivated. So spring, spring, dashpot. That's the mole structure that we have. And in order to get the stress to go down after yielding, what are the options we have? Well, we can make the spring soften at larger strains, or we can make the dashpot become softer at larger strains. So those are the two choices we have. It turns out that for robustness and easiness, it's usually better to manipulate the viscoplastic spring, the dashpot element in this model. So that's what I will demonstrate in this case. We will also later on talk about how you modify the modulus aspect of it. So here are the parameters. The first network goes from parameter 5 to 10. So these are the yaw hyperelastic parameters. These look fine. The second network is the network which has a spring and a dashpot next to it. So these are the parameters there. So these look good. The dashpot we want to play around with a little bit here. I'm not going to go through in detail in this video all the features here, but I want to mention that the parameters of interest for us is this one, FFF and EPS-F. FFF is how much the yield stress changes with plastic strain. So the yield stress you can think of is this number here, 61. It's sort of the value where the stress should start rolling over. And FFF specifies the factor that which this stress will evolve to as plastic strain increases. So we want it to go down a little bit. So I'm going to make it 0.8. And I want it to take about maybe 5% strain for the stress, the yield stress go from this value to 80% of that value. So this is a good guess of what's going on. I'd say run once. And this is now the predictions from the material model parameters here. Clearly it's not quite right. The error is 12.3%, but it's not such a terrible situation. We can certainly improve this, and let's see how we would actually do that. I often find it easy, of course, to just run calibration, but it's good as you work with the M calibration software or any material model for that matter. To get used to what do the parameters do. And that's really easy to explore here. So I'm going to say, well, one thing that I noticed is that to predict the strain rate dependence, the dashed lines here, they're too separated. And experimentally, they're more close together. So what do? Well, I'm going to try to reduce the strain rate dependence. And if you think about it and look at some of my other videos, you will see that you can achieve that by increasing the MM value. So I'm going to see if I can make this, say, 15, and we run it once. And we'll see that the difference between these two is much smaller here. So that's good. We like that. And that's kind of a good starting point, I guess. We can see that the yield stress is a little too high, and it's a little the drop in yield stress after yield is a little too quick. But we could start running this calibration from this point. In a situation like this, what I would do is, well, the parameters are good, but they're not awesome. So I would actually not go with the automatic method first. I would switch over to a slow and careful calibration where it tweaks the parameter one at a time to get it to better align with the data. And then I turn on the more powerful extensive method, which takes a little bit more aggressive searching. But I don't want it to search too much. Because I kind of like the ratio or the relations between these parameters that I have here. So we'll let this sit for a few seconds while we'll see what's going on. The error was 11%. Now we're down to 7% or so after a few iterations. So this is what I was thinking. It's a good idea to start with a careful, controlled initial calibration. So there will be no major changes to any of these parameters, but it will adjust them a little bit in order to better match the data. Once we have a little bit more control like that, we can go ahead and turn on the extensive calibration. So I'll stop this one right here. And that's kind of a good starting point. I could run this much longer. And if I did that, what will happen is I will save this and I will open my saved answer. So this is the TNV 2-network model answer that I created. I run this once, and this is the best I could come up with this two-network model here. So what's interesting is that the response when we have two parallel networks, this is important to remember, you have an initial elastic response, and then you have the onset of plasticity, which in this case has a yield drop associated with it from this FFF parameter. The fraction of the reduction is 0.73 here. That's what we see. But to get even better predictions, we need to actually activate more than two networks in this case. So this is a two-network implementation of the TNV model. And it works reasonably good, but it's not as good as we can get it. So I will see if I can improve this a little bit. So what I will do is I will switch over to another model that could be perhaps used for this, and that's the Three Network model. The PolyUMod Three Network model is a very specific model that works very well for many thermoplastics too, and it uses a very different approach to handle reduction in stress after the yield point. So here are the parameters for the Three Network model, and if you run it once, I already calibrated this. Apparently I didn't save my results too much, so we can improve this though. What we need to do here is we need to figure out the predicted values are too high, so I will have to reduce the yield stresses. So there are two viscoplastic networks. This is pretty easy to fix. One is 28 megapascal, and one is 60. So the first onset of yielding occurs early, and then it's a large-scale yielding. So I want to reduce both of these, maybe down to 15, and I make these 30, and I run it one more time. We'll see now it's a little bit more in line with what it should look like. That looks pretty good. And then I think what we can do is we could just let this run and calibrate from this point. But the purpose here is not to just watch it calibrate, but to understand what we are trying to achieve. So for the Three Network model, the yield reduction comes from mu BI and mu BF. So if I go back to our website and we take a look at the Three Network model, the Three Network model has three parallel networks as well. It's the same rheological framework, but the reduction in stress comes from a reduction or change in the stiffness of the spring of the B spring here. So there is no feature to evolve the yield stress in the Three Network model. That's a feature that's only in the newer TNV model. So that's why in this case, mu BI is the initial modulus, and then it evolves to a lower value, mu BF. And beta is how fast the modulus evolves to a lower value. So let's just run this for a few seconds as well. I'm going to start with a low, slow, careful calibration from this point. The error is 4%. It's not yet as good as my prediction with a TNV model with two networks. So we have three networks now, so there's a better chance that this will do a little better. And when I ran this, it did indeed give a slightly better result than the two-network TNV model. But I will instead of showing that, I want to show you the final and the best model that I have for this kind of material, and that's the three-network TNV model. I would, as I mentioned, recommend not using a modulus reduction approach that's used in the TNM model. Instead, the more robust and the more accurate approach is typically to use the yield evolution approach that's available in the TNV model. So here's my final calibration for the TNV model with three parallel networks. One is the hyperelastic network, and two of them are viscoplastic. The error is down to less than 2%. So if we look at the parameters here, we can see that the first network is given by these 6 parameters here, yaw parameters. This is a very low modulus. That's because the slope over here is very small. This parameter controls the large strain slope. Then we have two parallel networks. 256 is this modulus value or stiffness value, and this is 119. and they are giving you the initial slope response here together. We have each of these networks have a yield stress associated with it. One is 25 and one is 29. They're relatively similar. The MM parameter is the strain rate dependence. It's about 10 in this case, which is very common. What's interesting though here, and what's driving the accuracy of this prediction is the FFF parameter that I talked about before. So 59% is the final value here, and for this last network, it's 76%. So you see, there's no need for both of these FFF values to be the same. They can be slightly different. And that allows us to capture the response a little bit more accurately. You can also look at the predictions here. You can kind of see the characteristic response of a three-network viscoplastic material model. That is, you have an initial elastic response, then you have an onset of a viscoplastic flow. So one of the two, in this case, viscoplastic network, starts to flow around here, depending on the strain rate. And that gives you this slope here. Then the final network, the last one, the third one, kicks in around here, and that gives you a reduction in stress. So you can kind of divide the stress strain response into these different parts of the material model that are driving the response in each of these. And because of this way of thinking about it, it's pretty clear that three networks is usually enough to capture the response as accurate as one needs. You could go to a four-network kind of model for this, but I have very rarely seen the need to do that, so I wouldn't recommend it. It's harder to work with a four-network model than a three-network. So that's why I typically recommend for thermoplastics, three networks is what you need in order to get good accuracy, but don't worry about going more than that for basic viscoplastic materials like thermoplastics. The final thing is a feature that I want to mention here, and that is in M calibration, you can check the stability of a material model. So if you haven't tried this is kind of interesting, I guess. You click on this icon here, which checks the Drucker stability. If you say evaluate, it checks if this material model that we have right now is stable. And clearly it's not stable. It's like it's not stable in tension. And it's because the stress goes down. So the point here is that material models for thermoplastics don't need to be stable. There is no requirement to satisfy a Drucker stability. Most hyperelastic material models that you use for rubbers, you want them to be stable according to this condition. But for thermoplastics, there is no need to it. So you can explore this and look at that, but it really doesn't make a difference because the experimental data is not stable either. That's the reduction in stress for an increase in strain magnitude. That's the definition of stability here, or instability, the way I said it. So those are the common methods that I would recommend if you want to predict a reduction in stress for a thermoplastic. You can export this into any FE solver you're interested in and use it in your simulations. This works really well. It's not too hard to do. You just need the experimental data. So I hope you found that useful. Let me know if you have any questions. Thank you.